So here, if I will see, I put depth of the extrusion as a 6.5. If I will change it, let's say 10, you can see the difference. See, okay. To my earlier 6.5. Okay. So to make 3D from 2D, we can use that option, extrude. So this is simple. So such kind of data is available. See? So temperature dependent property, thermal conductivity, specific heat, density. Okay. So whatever material, then this is for type 6 L4V only. Okay. So you want all property temperature dependent, you can insert it. Okay. So literature data is many times available. Okay. So this is from one of the journal paper. Right? So from literature you can take the required data of the material. Right? Or if you have test data of your own, that you can insert it. So this is about material. Once you define the material of subroutine, or even with implicit also I go, deflux support, both this heat transfer is also support here, implicit and this implicit also. Both are like different techniques, but both support our deflux subroutine. But if you are using V deflux, means we are doing explicit analysis and then select it. Give appropriate time. Okay, and okay. Request appropriate field outputs, as here we are doing heat transfer analysis. Any of stresses, strains, displacement not needed. So we can, only we are interested in the thermal part. Let's say nodal temperature, heat flux. Just press OK. So required output we can select from this option, field output. So we can create new if you want. I will show you how. From this option, a required output for the thermal analysis is the nodal temperature. Our workpiece on the table like this. And in all other direction, it is free to expand in all direction like that. Okay. So apart from that, although we are giving heat flux from the subroutine, but still we need to define some unit load from here. Okay. So I will show you. Already I have defined, I think deleted. Okay, I will show you. So load 1, let's say we call it as a heat flux. Okay. So in thermal loading, what kind of heat flux we are showing? Surface heat flux, right? So surface heat flux will apply. Where? This surface. Okay. What is the magnitude? Magnitude I am not taking from here because that is a not stationary heat source. Magnitude I will take from the subroutine. Okay. So just as a default value, some 1 I will put, some unit magnitude, but don't worry, if I will put it blank, it will show some error. So some unit magnitude I will keeping, but the surface heat flux definition I will take it from the subroutine, not from here. This definition Abaqus provides for the stationary heat source, uniform heat source. See, if I will apply, it will show some arrows, right? Means it is applying some heat source. Okay. But when I will call subroutine, this definition will be rewritten. Okay. It will be overwritten. And the data will be taken from the subroutine. Okay. So just for the understanding purpose, how we apply the surface heat flux? Apply from here, create load, go in thermal, apply surface heat flux, choose required region and give some default value. That's it. Okay. And initial condition is also important. See, create a predefined field. Initial condition, what is initial condition? I shown on slide. At time t equal to 0, the whole model should be at the room temperature. That is the initial condition. So go in order, choose temperature, continue, select whole region and define magnitude. That is a 25 degrees Celsius. Right? So in this way, I will repeat it. And the technique is a structured technique. Okay. And most importantly, check your element type. This is the option. Check your element type, select it. Okay. See, coupled temperature displacement is our element type. It should have temperature degree of freedom. Here is the temperature degree. So the element name is C3D8RT. It is a 8 node thermally coupled. It results. You can see. I will show you first video. How my moving heat source we can see. See, the laser beam is moving and it is conducting heat. From top view I am showing. I will show you cut view also. Okay. The y direction I will take cut. And I will show in the thickness direction. See how the laser beam will travel. It is like a sine or cosine path. Right? At any point of time, we can check temperature. Let's say I will check my temperature on some of the peak. Let's say I will go. They have even shown the path also. See, like this. We are getting exactly like this. These are thermal images from the experimentation. We also exactly get same. If I will show without mesh, it will be more clear. See.